Hello everyone. In the last video discussed about the convolution integral, and today we will discuss some problems related to convolution integral. We already discussed about the derivations of convolution integral, and we solved problems on the convolution integral, that is I considered both are infinite signal here. It is h of t is equal to u of t and x of t is e to the power minus 8 into u of t. So now we'll consider the one as finite signal and the other one is infinite signal. We'll perform the convolution between that. So here the h of t is given by e to the power minus t into u of t, and x of t is equal to e to the power minus 3t into u of t minus u of t minus 2. So here h of t is a infinite signal, whereas x of t is a finite signal. The output y of t is given by the x of t star h of t. It is written as the integral over minus infinity to plus infinity x of tau into h of t minus tau into t tau. Now in given equation, that is h of t, replace the variable t by tau, so h of tau is equal to the power minus tau into u tau, and x of tau is equal to the power minus 3 tau into u of tau minus u of tau minus 2. I'll substitute that in y of t equation. Therefore, e to the power minus 3 tau into u of tau minus u of tau minus 2. Another one is e to the power minus of t minus tau into u of t minus tau into t tau. And the integral variable is tau, so I'll take e to the power minus t as the outside constant term. In simplification, we'll get integral minus infinity plus infinity to the power minus 2 tau into u of tau minus u of tau minus 2 into u of t minus tau into t tau. I'll plot the two signals here. Is u of tau minus u of tau minus 2, consider as one signal, and the second signal I'll consider as u of t minus tau. To plot u of tau minus u of tau minus 2, first I'll plot u of tau. I know the definition of unit step signal, and it is defined, its value is 1 for tau greater than or equal to 0, its value is 0, tau less than 0. And similarly, u of tau minus 2, it's defined, its value is 1 for tau is greater than or equal to 2, its value is 0, tau less than 2. If I'll subtract the two signal here, then I'll get u of tau minus u of tau minus 2. So you get a rectangular pulse with the width is 2. The second signal I'll consider u of t minus tau. First I'll plot u of t plus tau, then I'll take the mirror image of that, so that you'll get u of t minus tau. And then the x-axis I'll mention the time indexed value as t. Now we'll consider the different conditions, and I'll move the second signal and keeping the first signal as constant. I move the second signal, that is from minus infinity to plus infinity. The first condition is I'll consider the t less than 0. In the figure shown in the diagram, that's the way that the value of t is less than 0. You can observe there is no overlap between the two signals. When there is no overlap, the output is 0, because anything is multiplied with 0 is 0. I'll move the second condition. I'll move the signal to the right, and I'll place the second signal in between 0 and 2. I'll place the t in between 0 and 2, in such a way that the t is less than 2, and at the same time t is greater than or equal to 0. I'll combine the two conditions, and I'll get the condition is 0 to 2. The t varies from 0 to 2. And here you can observe there is a the overlap between a signal. The overlapping region is mentioned there, and there is overlapping region, and it is from 0 to t. That overlapping region will be mentioned in the integration. So y of t is given by e to the power minus t, the integral over 0 to t e to the power minus 2 tau into t tau. Integrating with respect to tau, we'll get e to the power minus t, e to the power minus 2 tau into the minus 2. Applying the limit, get the answer as 1 by 2 e to the power minus t minus e to the power minus 3t. Third condition, I'll place a second signal in such a way that t is greater than 2. Further, I'm moving to the signal to the right, second signal, and there is a overlap. The overlap region I mentioned. The overlapping region is from 0 to 2. 0 to 2. And that I mentioned in the integration limit. So my equation is e to the power minus t is integral of 0 to 2 e to the power minus 2 tau into t tau. After integration and applying the limit, I'll get the answer as 1 by 2 e to the power minus t into 1 minus e to the power minus 4. So therefore the output is given by its value is 0 for t less than 0, and when it's from 0 to 2, its value is 1 by 2 e to the power minus t minus e to the power minus 3t. When t is greater than 2, its value is 1 by 2 e to the power minus t into 1 minus e to the power minus 4. And the next problem we'll discuss about both are finite signals. So here I consider x of t is u of t minus u of t minus 3, and h of t is u of t minus u of t minus 2. So both are unit step function, and here both the signals are finite signals. Now I'll draw x of tau first, then h of tau. So x of tau is just replacing the variable t by tau, and h of tau is replacing the variable t by tau. So u of tau minus u of tau minus 3. Similarly, h of tau is u of tau minus u of tau minus 2. So the y of t is given by the integral of minus infinity plus infinity x of tau into h of t minus tau. So I'll draw x of tau. If I'll subtract u of t and u of t minus 3, I'll get the rectangular pulse. The duration is from 0 to 3. The width of the signal is 3. Similarly, if I draw h of tau, that is u of t minus u of t minus 2, and again here if I subtract the two signals, I am getting a rectangular pulse with the width is from 0 to 2 with the amplitude is 1. But in y of t equation, I need h of t minus tau, h of t minus tau. So I'll draw h of t minus tau, but considering t is equal to 0, so I'll draw the mirror image of h of tau, that is from minus 2 to 0. Then I'll add t to the lower and upper limit, so I'll get t minus 2 to t. Now the time index value is very important while shifting the signal. So t minus 2 to t, h of t minus tau. Now I'll keep the first signal as fixed signal, and second signal I'll move from left to right. And the condition 1, when I consider the t less than 0, in case when t less than 0, you can observe there is no overlap, the output is 0. Now here you should observe the width of the signal. The width of the first signal is 3 and the width of the second signal is 2. Okay, now for a condition 2, consider that t is in between 2 and 0, 2 and 0, 2 and 0. So t is less than 2, at the same time t is greater than 0. So we'll combine that, we'll get t is in between 0 and 2. You can observe there is an overlap between the two signals. The overlapping region is mentioned from 0 to t. So I'll substitute in the limit. So I'll get y of t is equal to 0 to t. What is the amplitude? Amplitude of both the signal is 1. So if I'll integrate that, I'll get a tau. So the answer is t. The third condition, I place t in between 2 and 3. 2 and 3. I'll just move the signal to the right and I'll place t is in between 2 and 3. That is t is greater than or equal to 2, at the same time t is less than or equal to 3. Now there is a overlap between the two signals, that is t minus 2 to t, there is a overlap. It's called the complete overlap. The complete overlap. and apply that overlap region in the integration limit. So t minus 2 to t, integration of 1 into d tau. So I'll get the answer as 2. Now case 4, I'll move the signal to the right in such a way that t is greater than 3. T is greater than 3. Same time t minus 2 is less than 3. So if I'll combine, I'll get the t is from 3 to 5. 3 to 5. So we can observe there is overlap between the signal, the partial overlap at the right side. So overlapping region is mentioned from t minus 2 to 3. So you'll get the output in that region. I'll apply an integration t minus 2 to 3. I'll integrate it. I'll get the answer as 5 minus t. And the last condition is both t and t minus 2 is greater than 3. We'll write t minus 2 is greater than 3, that is t is greater than 5. You can observe there is no overlap between the two signals, therefore the output is 0. So when I'll consider both are finite signals, generally you'll get 5 cases. In the first condition, generally not having the output is 0. The second condition, you get a partial overlap at the left side. And the third condition, you'll get a complete overlap. Fourth condition, you get a partial overlap at the right side. The last one, no overlap. So when there is no overlap, the output is 0. Other condition, based on the overlapping region, you have to integrate that and applying the limit answer y of t. So this is about the problems related to convolution integral. Thank you.